Hello, everyone. Thank you so much for your awesome response for my YouTube channel and amazing comments and your valuable suggestions in this area helped me a lot to complete 25 episodes. As you all know, recently we have completed our 25th episode and we are entering into 26th episode. And as you all know, our main objective is to interact in terms of health, education, and lifestyle. And all the global experts in this area are invited into this podcast, and we are interacting with them regarding all these pointers. Today, we have one of the young and dynamic, eminent guest, none other than Arth. So, he is a very good speaker in the area of quantum computing. So, if I introduce him, he is the MIT Media Lab researcher and very much interested towards quantum computing and astrophysics. And he has educated more than 1,000 students who range from IISc Bangalore to IITs and other institutions, prestigious institutions. He also runs his YouTube channel and very much enthusiastic towards quantum computing. I have read his posts in LinkedIn and I'm very much amazed with his knowledge. So today we will be discussing about the hardware part of quantum computing. So now I am sitting in front of my laptop. I know what is classical computer is, what are the components of it, but we have an excitement. We have a kind of dream, imaginary world for quantum computing because as of now it is not a reality in our location. And as you know, hardly we have one quantum computer in our India as per statistics. So in this scenario, and seeing the wide popularity of quantum computing and lot many people joining BTech course in quantum computing because some of the universities are starting their quantum computing course in BTech, and also MTech program is also being planned. So I thought, like, why not we have a discussion on hardware part of quantum computing, and our eminent guest Arth will be definitely helping us to know about all these details. So on that positive note, not wasting your valuable time, just wanted to tell you all that please do like, share, comment on this podcast, and do let us know your valuable sessions. Based on that, I will be framing my forthcoming sessions. So, on that positive note, let us have a discussion with Arth. Thank you, Arth, for joining our podcast series, and it is great to have you in this session. So, can you
Thank you
please
for inviting
introduce
me.
yourself to my audience?
Yeah, so first of all, hello everyone, and thank you for inviting me here. And I would say I'll encourage you guys to like and subscribe, just like Rajesh asked you to. Uh, so I am Ansh or Earth, so whatever name you know me by. I am an independent researcher. So I work in the field of quantum computing and artificial intelligence independently. So most of the things or research paper I write are written independently. Some of them got selected to few of the top IEEE conferences too. And mostly my area of interest lie in STEM. So yeah, like this is my area of interest. Other than that, I love to read books and yeah. So if you follow me on LinkedIn or anywhere else, you'll get to know like about either books or about quantum computing, which I keep posting about on my LinkedIn. So,
Yeah, so nice to know. Here in this aspect, can you please let us know the difference between classical computer hardware and quantum computer hardware?
yeah, for sure. So basically, like everyone of us study in our, like third to sixth grade, like our normal classical computers are working on binary digits or bits, right? So what are these binary digits? These are the combination of zeros and one. This is what we read, but how quantum computer is different from this is basically utilizes something called a qubit. So qubit is basically based on the principles of quantum mechanics. So a quantum computer is basically based on a principle of harnessing the quantum mechanical properties of nature and building upon it. So, just like we harness the normal classical bits of zeros and ones, here we have a third state which is called superposition, and superposition has like infinite number of possibilities within the range of this zeros and ones. So it could be anything probabilistically between zeros and one, and this is how it's different. So building a classical computer is fundamentally different from a quantum computer, because classical computer harnesses the principle of classical mechanics or the Newton's law, where everything is very much certain. But in quantum mechanics or quantum computing, things are very probabilistic, that you cannot be very sure of any of the parts.
Yeah. So, can you please explain the main physical systems used to build qubits, like superconducting circuits, trapped ions, photons? So we know most of them, but can you please do let us know in a elaborative manner?
Yeah, for sure. So we have different kind of hardware. So first of all, I would like to point out, like just like our classical computers have a standard hardware, we do not have a standard hardware in the quantum computer. So different research and different companies utilize different types of hardware itself. So there's superconducting qubits, there's trapped ion, there's photonics, there's diamond NV, and so many other types of like qubits which are being made. So every kind of different hardware has its own pros and cons, which is different from each other. And yeah, so for example, superconducting use electrical signals, and just like a very much similar to how it is used in chips. But let's say if you go for diamond NV, right? So it uses nitrogen valence electrons, and if you go on the side of photonics, it utilizes something of a photonic property. So, for example, photons have this specific thing known as spin. So it could be up and down, but there's a different polarization property, where polarization refers to, it could be rectilinear or it could be diagonal. So these different parts can be utilized in these photonic space quantum computers. So, yeah.
Okay. So, can you please let us know how do we decide which physical system is better for building scalable quantum computers?
Yeah, so there are actually different criterias. There's no one standard way to decide like which system is the best. Every like hardware, as I said, like superconducting and trapped ion and photonic, everything has its own pros and cons. There are five standard criterias which are mostly used to decide like which one could be good for it. Okay, and it's known as DiVincenzo criteria. So I hope I'm pronouncing it right, but it's basically yeah, it's known as DiVincenzo criteria. It deals with coherence time. Like coherence is basically, imagine qubits to be a coin, okay, and if you're spinning something on, let's say you're spinning this coin, so how long it's rotating and how long it's useful, okay, that is coherence time. And then we have something like gate fidelity. So gate fidelity refers to when how accurate your gate is in terms of comparing it to mathematical equations. So for example, all the time, like we deal with linear equations when we are dealing with the quantum mechanical part of quantum computing. So in that, we are actually calculating the states even using pen and paper. So how close the answer is of the quantum computer to that answer which you can decide on pen and paper, this is called gate fidelity. And there are other criteria also, where we have connectivity, scalability, and other things. So these are some of the criteria how you decide actually which could be a good quantum, how you can decide a hardware.
Oh, okay. So, what challenges in maintaining qubits, especially issues like noise and decoherence?
Right,
What
right.
do you say on that?
Yeah, so noise and decoherence, there are like two concepts. So noise and decoherence basically refers to what could be happening within the system that can interrupt the qubit. So how I imagine in my head, it is like, imagine to do this quantum computation, you need a very stable water, or water in a pond or water in a lake. And every noise and decoherence are like if somebody throws a pebble or a stone into the water. So these ripples which are happening within the water is like noise. and this affects the quantum computing answers. So we are currently living in the NISQ era of quantum computers. So but yeah, so over a period of time, there are different ways which we'll figure out to reduce this noise. So currently what we do is we have a physical qubit or a robust qubit, and we create logical qubits. So we basically do not have to deal with this part of not measuring the qubit all the time. So for example, whenever you measure a qubit, it's going to collapse its state, right? So it's either collapse to 0 and 1. So one of the ways we use or utilize the qubit is to actually create copies of it, but also at the same time we cannot create exact copies because of something known as no cloning theorem. So this is what is happening in these noise correction and or decoherence part. And apart from that, like these are the ways of error correction or methods of error correction in quantum.
So here I wanted to know, for example, when we purchase a classical computer, in general, we think of memory, we
Right,
think about input-output devices, we
right,
think about cache memory.
right,
So all these aspects we think.
right.
So if you take a quantum computer, what are the internal components of these quantum computers? Can you give
Mhm.
us a brief overview about them?
Okay, yeah. So as I've said, like there are different components of different quantum computers. First is where you are utilizing or harnessing a physical state. It could be anything like superconducting to any other parts, but most of the quantum computers have something called a diffusion refrigerator, which is basically a cryogenic to cool it down to. So basically, think about it like as I've just said that there are a lot of noise and decoherence in quantum computation. So one of these reasons why these noise happen like internally, it can happen within the pulses or electrical pulses occurring within the system. Or the other ways is like of heat. Imagine heat getting transferred, so that's why you need to cool it down to millikelvin temperatures, right? So for that we have diffusion refrigerator or cryogenic systems to cool it down so it doesn't create error. So if you just think fundamentally what heat is random vibration of atoms within a system. So that's how heat happens or heat gets transferred, right? So we make sure that this heat doesn't get transferred. So most of the quantum computers have different components, but one primary component which you are going to see commonly, sometimes it's not the most important part because like photonics based quantum computer may, people say it works in a room temperature, but it also requires a somewhat a diffusion refrigerator. It doesn't require as much of low temperature as a normal superconducting or trapped ion quantum computer may require, but still it requires a very cool temperature to work on accurately. So these are the I think the main component is like apart from the general hardware could be a diffusion refrigerator.
Okay. So here I wanted to know uh, the most general terminology we hear is about quantum error correction. So can
Right.
you please let us know what is the concept of quantum error correction and why it is so critical for hardware development?
Right, right. So, as I've said, like there are a lot of noises. This is why we are currently living in the NISQ era of quantum computers. That the hardware which we are utilizing is deals with a lot of noises and decoherence from the outside world, or it could be from within the system, depending on what kind of system you're using. And like it could be always like depending on the system architecture or design of the quantum computer. So in this case, quantum error correction methods basically help quantum computers to work despite of giving a lot of errors. So like even if there are errors like the logical qubits or imagine these quantum computers could be very powerful. So how I see all these things like of quantum error correction is that when you think about quantum computers, we can have quadrillion possibilities at just 50 qubits. And IBM's biggest quantum computers have, I think, 1121 qubits, but still we don't have enough powerful computers just because of this qubit, this error, like noise problem. So why? Because when you see this noise problem, is that basically to solve this, we have to create redundant qubits or logical qubits of the main physical qubit. So to solve this error problem, what we are doing is we are slowing down the process, but the means of error corrections allow you to run these things despite of showing multiple errors. So Quantum error correction basically refers to the method of how you correct this error despite of or how you run a quantum computer despite of having random noises, or you can say decoherence from outside or within the system. So at the end your quantum computer will work despite of noises. So we are currently in the NISQ era, and we are still figuring out in the hardware how are we going to locate or how are we going to fix these errors. But hopefully this is one of the things which I'm looking forward in future, that more quantum computers, as we scale more and more, we are going to see less noisy quantum computer, or we will figure out a way where these errors are almost none. I'm not sure if we are close to it, but I'm pretty sure like in future, if we keep scaling it to it, like we'll get to see something like that.
Very nice, sir. So I wanted to know about how do this cryogenic systems and extreme cooling enable quantum hardware to function. You already mentioned about it in your previous in our discussion, but can you please elaborate?
Yeah, sure. So basically, there is, you can imagine like most of the component. Okay. So one thing I would just give an example of is a wire. Okay, so we all study resistance in our like sixth grade or ninth grade, whenever you start learning about heat in wires and electrical system. So imagine you are flowing current to your quantum computer, and the heat is also getting transferred via those currents, or some kind of resistivity is being created, and resistivity is basically the reason why heat gets generated, right? To cool it down, we need cryogenics, and this cryogenics is basically keeping this computer within this diffusion refrigerator, or whatever system you are using, like whatever hardware you have. It basically cools it down to the absolute 0 or milli Kelvin temperature. So this heat doesn't throw a noise, and this diffusion refrigerator, like I think recently Bhava Atomic Research Center got one from Oxford. I'm not sure, but Oxford basically donated to it. Some of the people who are working in like these atomic center, like, are my friends, and I just get in touch with them about like these quantum computers. Even though we only have statistically one main quantum computer in India, probably you can say QPI AI's quantum computer. But apart from that, like there are a lot of government projects. I think DRDO for sure will be working on their kind of hardware, and different things will be working. Different organization will be working for their own quantum computer for different advantage. But at the end, like we all need diffusion refrigerator, and these diffusion refrigerators are nothing just to cool down so your quantum computer can.
Okay. So we have interconnects. What role do interconnects and control electronics play in scaling quantum systems?
So basically, these are for like let's say you have to control these system. Interconnect plays basically help you to sometimes read these answers or these inputs from quantum computer, and it helps you sometimes control or manipulate the system which you are working within the quantum computer. So imagine we have how I imagine it in a classical system, not in the hardware side, but if you think about even the software side, we have like basic CRUD operations, right? So create, read, like update or delete, something like that. But you just think you have a read or write operation or manipulation operation. So something similar for quantum computers. So these quantum computers also need some kind of controlling system, and how do you actually understand what the input is, output is. So interconnect plays basically deals with that part of quantum computing.
Oh, okay. So, how do researchers currently measure the performance of quantum hardware? Because performance measurement plays a vital role. So, what are the
Right.
metrics like gate fidelity, coherence time, or qubit count? So, what is the measurement of the hardware?
Right. So, as I've said, like previously, that there are different hardwares and different, pros and cons. Different pros and cons for different kind of quantum computers. So we are still working on like what should be the standard, but no single hardware has all the pros or all the cons. So we are using mixed systems currently. So we are thinking, okay, so if we can work on something like topological qubits, which is basically used in Majorana 1 by Microsoft. So are its what is advantages. It's very scalable, but it also comes with its own disadvantage. So maybe like when you think about photonics or platon, it cannot be made so small right now, so it cannot be very scalable for now, as in comparison to something like a topological qubit, like a Majorana chip. So if you have seen the Microsoft's Majorana one, it's this small, right? It was launched, and it was said that okay, this is going to be the Intel moment, or like how Intel launched its first chip, something similar to that for quantum computing. Right now, I'm very much suspicious about personally topological qubits, because a lot of research papers have been out after that period that maybe topological qubits might be not very good for simulating these qubits. But we are still seeing development, so we cannot be sure. And it had a lot of I think buzz around it. I think quantum computing in itself is a lot of buzz, so people think, and like there's a lot of hype around quantum computers. We have not seen anything of a quantum advantage yet, but I'm pretty sure that we'll get to see one in 5 years for sure. So yeah, so like this is like I as I just said, I would like to summarize that there's no standard way of which you can say okay, this is the only way where you can decide this is a good quantum computer. But like as I have explained, gate fidelity, which is basically how accurate your like predictions of gate is in comparison to math, or other parts like coherence, which is how long your qubit is going to be relevant, and different parts of scalability and qubit can all these matters, and all these coming together matters also. So I personally imagine a hybrid quantum computer. I always say in most of my classes that in future we are going to see more of a hybrid quantum computer, not just based on one single hardware. So probably something might be utilizing superconducting and photonics at the same time to deal with quantum computing, and that might be more useful in comparison to how we see a pure quantum computer, right? So we cannot see a single hardware, but maybe a mixture of most of it, and maybe a mixture of even classical computers, because there's something like a optimization problem that can initially first be better solved by quantum computers, and then you can use a classical computer to actually understand it further. So yeah, I'm pretty sure like most of the quantum computers even in future are going to be somewhat a hybrid one, not just a classical one, because of this reason.
So, here, can you please let us know, as you are doing lots of research in this area, what innovations are happening now to bridge the gap between laboratory prototypes and industrial scale quantum machines?
Right. So there are a lot of developments happening. I'd say there are, if you think about major companies like IBM, Google, Microsoft, everyone wants to enter in this market, and there are different techniques which are being developed, different algorithms are being developed. I'm more interested in the uh, software side personally, but I know like hardware does need a lot of development and R&D still. What I am personally excited about is how different quantum algorithms will be built in future. That's my like main area of interest, and how it's going to help in ASI. So I'll answer both of them one by one. So first of all, for algorithms, just think about solving these big problems like traveling salesman problem, right? Which is measuring each node once without visiting one again, and making sure like you cover all the nodes, right? So this is a NP problem, like PNP problem, and it grows exponentially. To solve this, we might need a quantum computer, and once we solve it, like and build an algorithm around it, we can also come up with problems which we thought required a very high amount of compute and can be solved with quantum computers. So maybe like there'll be an algorithm, better algorithm from for drug discovery, just like we get to see in Google's AlphaFold, or it was going to make game development more efficient. So one research paper which I'm working on is basically how cloth simulation is very hard when you use classical computer. But maybe if we utilize one component of a quantum computer for like the closed simulation part, we can create a lot of random numbers, and we can actually simulate this clothing effect with less amount of compute using quantum computer. So maybe in future, if we get to see more quantum computers, we may see it even in game development side. So that's the first thing. Second thing, which is ASI, which is artificial superintelligence. I think it's not me, but a lot of people like Eric Smith, who's the ex-CEO of Google, and Demis Hassabis, who's the uh, person like behind Google DeepMind. So all of them said like we are going to see probably artificial superintelligence in 10 years. I'm pretty sure if ASI comes into existence, there will be some part of quantum computer being used into it, or like the first thing which will be used to the high increase the computation power of these ASI would be probably a quantum computer. I'm not sure what kind of hardware it would be, but like these two are the main areas where I think like which I am very much excited about. So primarily somewhat game development and algorithm part, and secondly like how ASI will be utilizing this quantum computer, because that's like where the future is headed towards. So yeah.
Yeah, let us wait and see for the future. Yeah. So, how do
Yeah.
you see the balance between hardware and software evolving in the quantum computing ecosystem?
Right. So how I see is like there's a lot of things happening right now in software side, and even in the hardware side. Most of the papers which I think I read personally are on the hardware side, because most of the scientists somewhat like who work in or enter in quantum computing, I think they have somewhat of a electrical engineering background. So we get to see more papers from that side. Even though now in last 3-4 years after IBM's Qiskit, I'm seeing a lot of algorithms implemented in the software side. But I'm pretty sure like different people are right now working in this hardware side and trying to figure out how can we actually reduce this noise and noise issue, and how can we actually get a better if and more efficient quantum computer than we have right now. So that's what is happening in the like hardware side. And in the algorithm side, I'm seeing that after like we have LLMs like ChatGPT, we have tools like Cursor. I'm seeing a lot of people, even in my classes, a lot of students do come like they tell me I'm working on quantum reinforcement learning and I'm writing this research paper. And when I see their research, I get to see, oh wow, that's great. And even myself, I'm working on like how uh, us like normal simulations, and comparing them with quantum simulation, and how quantum simulations can be better used in even financial modeling, like something as simple as Monte Carlo algorithm. So in there, if you use a quantum computer, how it can be more efficient. So I'm seeing right now a sudden growth in the software side and from last 4 or 5 years. But I think there's a lot of development needed in the both of the areas. So whatever areas excite you, I'll say just get in and like get your hands dirty and do something in the quantum world. So, yeah.
Yeah. So, in this context, I wanted to know what real world applications will become possible once quantum hardware reaches fault tolerance.
Right. So one thing which I think about is for sure is how we solve first of all these optimization problems. So as I said, like traveling salesman problem, so right now companies spend millions and millions of dollars to get this data of, like, let's say so for the people who are not familiar with it, traveling salesman problem is a very common problem. How, let's say, your Zomato driver or how your Swiggy or Zepto orders reach to your home. So there are n number of nodes given in a path, and there's always a shortest path. But to compute that shortest path, your classical computers need a large amount of compute, and even sometimes not like a very correct answer, because it's an exponential growth PNP problem. So you will be probably seeing here the first applications of it, and I'm pretty sure like people will be seeing application in quantum cyber security part. So where we might be having, I think NPCI is working currently on QKD part of quantum, where in a post quantum world where we have quantum computers, how we can be still be safe, how our financial system still can be safe from other hackers of a world. So imagine, let's say China builds the first quantum computer, and let's say it scales it to 10, it creates 10 copies of that quantum computer and give public the access of it. So there will be a person sitting around who wants to do create malice in the world, and what they are going to do is going to hack banking system in different parts. So for that, you will be using quantum computers to even save yourself, where the the harming part is also the quantum computer, but also saving part is the quantum computer. So a fault tolerant quantum computer is going to first of all increase the speed of computation. So all these brute force method, how you crack these parts of your like email accounts or something, will become very easy. So to get safer from it, we'll use something like BB84 protocol, or yeah, something like that. So yeah.
Okay. So, you know, look, it's you most about the future of quantum hardware in the next 5 to 10 years. So that is
Okay.
like what excites you about the future of quantum hardware in
Mhm.
these quantum computers in the coming 5 to 10 years?
Oh, so one thing, it's very much my personal opinion. I don't think so. I will be right or wrong, but we'll get to see like in future that I think uh, right now the current technology which we are working on, like Majorana one and all those things, a lot of these hardwares will actually obsolete, and maybe two or three primary hardwares will emerge. So maybe something like a superconducting qubit, or mixture of superconducting or photonics. I am very much pro photonics person. So I think like if we build photonics kind of quantum computer, it will be cheaper in comparison to normal computer, and probably we can actually scale down these. Right now the photonics quantum computers are very big in size, but we can also scale it down and maybe use lasers within a laptop. So for example, maybe in not in 10 years, but 40 years, we might be having something like just like we have CPU and GPU, we might be having a QPU, so quantum processing unit within a laptop, which will be this small, and will be using probably a mixture of superconducting and photonics qubits. So I'm very excited to see that. And different countries are like in the race, and I think China is very much ahead of most of the countries which are working on this system. But my personal opinion is I just want to see like which are the quantum hardwares which still stay relevant in the future. So yeah.
Yeah, we are also excited in this aspect. Thank you so much, Arth, for spending your valuable time and giving us excellent pointers in terms of quantum hardware. As this is a emerging field and people are very much interested to know in this aspect. This podcast will definitely help them to know the features of hardware and how to uh, gain the better knowledge in terms of quantum hardware. So, thank you so much for giving us all these valuable insights and sparing your valuable time.
Yeah, thank you very much first of all for inviting me, and also spending your precious time with me so to ask these questions. So yeah, thank you very much.
Yeah, thank you so much.
Thank